Hi everyone, welcome back. We're going to talk about chi-square tests, which happen to be one of my favorite tests, not just because I like them, but they're used so widely in epidemiology and public health that just learning to use chi-square tests and 2 by 2 tables or contingency tables can do a lot in epidemiological research, where we look at exposed groups and we want to determine the risk of a certain outcome. And in chapters 1 through 3, there's a lot of discussion about calculation of relative risks and odds ratios, which are often effect measures that we use in public health and epidemiology to say what the risk is associated with a certain exposure, or conversely, the benefit that would be associated with an intervention. And so 2 by 2 tables and contingency tables and chi-square tests are kind of the lifeblood of public health and epidemiology. I've heard epidemiology described as the science of long division, and I don't take that personally as an epidemiologist, but in some ways we do a lot of long division, and we do calculate a lot of relative risks and odds ratios, which are most easily calculated from a 2 by 2 table, but we can not only get those effect measures, but we can also do formal statistical tests to see whether there's an association that's meaningful. We can also calculate confidence intervals around estimates like relative risks and odds ratios, which your book goes into in great detail. Again, we would allow our computers to calculate those for us, but the concepts are very similar to what we're going to learn today, which is how to set up a chi-square test, primarily for a 2 by 2 table, but we can do it for actually any cell counts. But the important thing with chi-square tests is that it's based on categorical data or nominal data. And traditionally in epidemiology, we would set up our data like this, where we'd have a 2 by 2 table, and we have our exposed group and our not exposed group, and our disease group and our not disease group, and create this 2 by 2 table. This is very classic design for a setup for a study in epidemiology, both for case control studies and cohort studies, where we would be interested in looking at the associations between an exposure and disease. And your book does a pretty good job of describing the difference between a case control study and a cohort study, but they are the kind of workhorses of epidemiology and public health as far as study design. So you should become familiar with this overall setup of data. So from a contingency table or a 2 by 2 table, we can calculate some pretty nifty measures of risk. In the case of a cohort study, we might calculate what's called a relative risk, where it would simply be, if we're looking at this 2 by 2 table, among an exposed group, what is the incidence of disease in the exposed group? So we could write that as A divided by A plus B, where A plus B is the total population, okay, that we're studying, and A, the numerator, is the number who develop disease. So A over A plus B would be incidence in the exposed, and then C over C plus D would be incidence in the non-exposed group. Okay? So when I said the science of long division, this is kind of what I'm talking about. But the relative risk then becomes an effect estimate of how much greater is the risk in the exposed group versus the non-exposed group. And as we'll see, and you should know as you get through your epidemiology courses, that a relative risk greater than 1 means that it's an elevated risk, and a relative risk lower than 1 actually means there's a protective effect. But we can calculate these effect measures without any statistical, formal statistical tests. But we would want to calculate a confidence interval around a relative risk to see if it contains the value 1. And if it doesn't contain the value 1, we can either say it's a protective effect or a potential risk factor. And we'll look at that more closely in a moment. So here's an example. We have a very small cohort, and we had 100 in each group, exposure and non-exposed. And this could be a randomized study, but we'll assume that this was just an observational study. And we had 20 who developed disease in the exposure group, and 80 did not. In the non-exposed group, we had 10 who developed disease, and 90 did not. And let's say we followed them for a year. Okay, so this is an incidence over a year. So we would say the incidence in the exposed was 0.20 per year, or 20% per year. And in the incidence in the non-exposed was 0.10 per year. Okay, and that's just 10 divided by 100 for the non-exposed and 20 divided by 100 the exposed group. Okay, calculate a relative risk. In this case, we say the relative risk is 2.0. And if this was an exposure, let's say high-fat diet, and the disease was cardiovascular disease, and so having a high-fat diet increases your risk of cardiovascular disease by 2.0, 2 times. Okay, so we're not going to get into interpreting relative risks too much in this class, but relative risks are a really important effect measure that we use in epidemiology, public health. And if you look at the literature, relative risks and odds ratios are often reported. So when we're talking about doing a chi-square test, it's to say, well, okay, we've got this relative risk of 2.0. Is this statistically significant? Okay, it doesn't tell us whether it's clinically meaningful or worthy of some sort of public health intervention, but it will tell us whether there's a statistical difference in the proportions that we find in this 2x2 table. We can also calculate a different effect measure called an odds ratio. And again, if you review chapters 1 through 3, it'll discuss the difference between an odds ratio and a relative risk. An odds ratio is something that we can get from a case control study. It's also a reasonable measure to use in a cohort study. And it's basically the same idea, except instead of calculating the relative incidence, we're calculating the relative odds. Odds are different than incidence, and it's a little confusing, but it's just the ratio of the diseased to the not diseased in the exposed group compared to the ratio of the diseased and the not diseased in the non-exposed group. So we don't often think in terms of odds, but for 20 to 80 odds versus 10 to 90 odds, if we take the ratio of those two, so 0.25 and 0.11, we get an odds ratio of 2.25. Notice that this is the same data, but we get a slightly different effect measure estimate from that data, 2.25. And what we'll see is that odds ratios tend to inflate the relative risk unless the disease is rare. So in a case control study, when we do a case control design, we will often do a study based on a rare disease. The first study that I ever worked on was actually an Alzheimer's case control study. And so when I say for rare diseases, for a rare disease, the odds ratio will be actually very, very similar to the relative risk. And that's because when A relative to B is very, very small, that means, let's say only 1% of the population, or less than 1% of the population, has a disease, it's relatively small compared to the entire population. So the equation that I showed you for the odds ratio of A divided by B is very, very close to A over A plus B when A is very small relative to B. Likewise, for a rare disease, C over D, the odds ratio, will be very similar to C over C plus D when C is far smaller than D, okay? So we can use odds ratios that we calculate from a case control study in a similar way as we would for a relative risk. Again, the assumption being that the disease is somewhat rare. So as an example, the incidence of homicide is relatively rare. It's not rare as it should be, but in terms of the overall scheme of outcomes, homicide is relatively rare. And so let's say the incidence is 10 per 100,000 per year. So we could do a case control study on homicide where we took cases of homicide and compared them to control and see what factors were different between cases and controls. And you'll see here that our estimates using an odds ratio or a relative risk are fairly similar. A over A plus B in the case of incidence would be 10 over 10, the 10 who have the disease or the outcome, plus the 99,990 who do not. And our incidence in that case would be 0.1%. Well, A over B, which would be the 10 cases per 100,000. So we're taking A over B instead of A over A plus B. It's very, very close to 1%. Okay, so it's because that 10 out of the whole in the population is relatively small. So the odds ratio is kind of a miracle in some ways that we can calculate from a 2x2 table from a very relatively small study, case control study. As long as it's a rare disease, it's a fairly good approximation of the relative risk. So yeah, odds ratio can also be a useful measure in risk in cohort studies. It somewhat overestimates the relative risk for common diseases. And so when I talk about this, odds ratios and relative risk, when we get to logistic regression and survival analysis at the end of this class, often what we're doing is trying to obtain adjusted risk estimates, adjusted relative risks, or adjusted odds ratios. And if we do survival analysis, there's something called a hazards ratio. But these are the effect measures, the things that we often describe in epidemiology and public health. And so I wanted to spend a moment to talk about how a 2x2 table we might calculate these effect estimates before we do a statistical test or calculate confidence intervals around those estimates. But conceptually, it's important that that's one reason we are so focused on 2x2 tables in public health. So the way we interpret a relative risk is that when the value equals 1, we would say that there's no difference in risk. They're equal. Risk, the ratio of one risk to another is 1. Okay? So not 0, but 1. Okay, for relative risk, that equals no difference. A relative risk of less than 1, we would call that a protective factor, or it actually decreases your risk. And often with interventions, our goal would be to reduce the risk, right? So a drug or a program or some other intervention, the goal would be to see if it reduces the risk. If a relative risk is greater than 1, we would say that it's a risk factor or it increases risk. And so something like radiation exposure may increase the risk of cancer. And if we had a relative risk of, let's say, 4.0 for those who routinely get x-rays versus those who don't, that would say that, well, you have a 4-fold increased risk of cancer. So that's how we interpret relative risks, and the same would be true of odds ratios. Again, an odds ratio can be somewhat inflated relative to a relative risk if the disease is not rare. But the odds ratio 1.0, that's no difference in risk, even odds. If it's less than 1, we would call it a protective factor, just like we would with relative risk, lower odds of disease. And an odds ratio of greater than 1, it's considered a risk factor. And again, this is review, and so this comes out of chapters 1 through 3. And this is somewhat independent from what I'm going to talk about now, which is the chi-square test for independence. But these are the effect measures that we often want to calculate as well. So a chi-square test of independence is more universal than for 2x2 tables. We can use it for any categorical variable against another categorical variable to see if there are differences in the proportions across those groups. So a chi-square test of independence is used for categorical outcomes. Usually it's disease, not disease, but it could be any number of categorical outcomes. And then we're going to have 2 or more comparisons within the other categorical variable. So the null hypothesis in a chi-square test is that the distribution of the outcome is independent of the groups. So when we saw the relative risk, that would say that the distribution of the outcome of interest or disease would be independent of being exposed versus not exposed. That would be the null hypothesis. The alternative hypothesis for a chi-square test is that there is a difference in the proportions in those cells in the group, that there is some dependence of the outcome based on the group you're in. So it's not exactly saying zero in the traditional sense, but it is saying no association. And the statistic that we use, the chi-square statistic, is actually the sum of the observed frequencies or counts within the cells versus the expected counts. And the expectation would basically be that the groups are equal. So what we observed against what is expected across the cells becomes our basis for this test statistic called the chi-square statistic. It is not the same as the t-test or the ANOVA, which have different distribution assumptions. A chi-square distribution, again, will have a different critical value that we use when we calculate statistics. Likewise, when we calculate degrees of freedom, to look that up in a table if we were doing it manually, the degrees of freedom would be the row count. So how many values do we have? How many rows do we have in our data? So if we had 3 groups, 3 categories, that would be 3 rows. And if we had, how many columns do we have? So for a disease outcome, yes, no, that would be 2, okay? So the rows minus 1 times the column minus 1 will give us our degrees of freedom. So that's how we would laboriously go about looking it up in a table if we wanted to get a critical value for a chi-square test. In a 2 by 2 table, it would be degrees of freedom would equal 1 because 2 minus 1 equals 1. Okay, so for other types of chi-square tests with multiple categories, we would just want to make sure that we look at the degrees of freedom appropriately and also pick an alpha level. And so if you look at table 3 in your textbook, in the appendix, you can actually look up a critical value. In this case, for a 2 by 2 table, the critical value is always going to be 3.84. For different shapes of tables, the critical value will be different. But ultimately what we want is a p-value, and we can have a statistical software program calculate a p-value for us, just like we did with t-tests. So I'm going to do some demonstrations now for both t-tests and chi-square tests to just kind of bring home these different points that we've had so far. Okay, so we're going to do a little bit of hands-on, or at least demonstration of what we're doing when we're running a t-test or running a chi-square test or running an ANOVA. And ultimately, our decision to use t-tests or ANOVA or chi-square tests really depend on the variables that we're looking at and their levels of measurement. In fact, picking the right tool is often based on the level of measurement that we have, and that's half the battle in statistics, is making sure that we're using a tool that's appropriate to our data, also appropriate to our research questions. So as a little bit of background, last week in the live session, I introduced this data set that I'm kind of playing with a little bit, which is the National Ambulatory Healthcare Survey. And this is the emergency department visits from a nationally representative sample of emergency department visits. And I chose to focus on a population of patients who had concussion. So that's the background in this data source. But I'm going to simply use this to demonstrate how to do a t-test, how to do a chi-square test. And sometimes we do these descriptive analyses to help us make decisions for multivariate analysis later. And in this case, I'm doing bivariate analysis to understand the associations among my variables. So these aren't ultimately my final outcome results, but I want to know the association among these variables. So I'm going to run some t-tests, I'm going to run some chi-square tests to do bivariate analysis. It does not have to be the final ultimate test of what our research is about. So I'm going to, as an example, under tasks and utilities, and again, I'm in the visual programmer mode within SAS. You'll notice here under statistics, I have data exploration and summary statistics, which is how we can go about getting our descriptives, which we did in week 1. We can also get some inferential statistics, such as confidence intervals for a proportion, confidence intervals for a mean. But we're going to get a little deeper now and start doing t-tests. We're also going to use table analysis, not just to get mean frequencies, but to do these contingency tables, which is crossing frequencies across 2 different variables. And that's where we're going to do our chi-square test. So notice it doesn't actually say chi-square test here. It's actually within the table analysis feature that we will find the chi-square test. So let's start with t-test because it's a little easier to find. Okay. And notice here it has different types of t-tests I can do. I can do a 1 sample t-test, which you're actually asked to do in your homework. I've got a paired test, which would be if I was looking at the same participant over 2 time points or some other dependency. And I'm going to use a 2 sample test. So you don't want to use the default setting here. We're going to do a 2 sample test. My analysis variable, I'm going to hypothesize that the age distribution of males and females is different. And I'm going to specifically say that the means of concussion are different for men and women. And I'm going to suggest that men actually have a higher average age, where the risk for women tends to decline precipitously with age, whereas for men, it will continue slightly later. So my hypothesis is that there's a difference between men and women, and that men actually have an older age of average age of concussion. I have no real basis for making this hypothesis, but we'll just go with that. But mostly I'm interested to see if there's any association between sex and my age. Okay, so my analysis variable is age, which is appropriate because it's a continuous measure. And my grouping variable is going to be sex. So I've set up a 2 sample t-test, age and sex. Let me see if there's any options I want to select. Okay, well, one is a 2-tail test. That's the default. I could set up a 1-tail test, upper test, meaning one group would be higher than the other. The other lower would be that it's lower than the other, but I'm just going to do a 2-tail test, which is fairly standard. Okay, and that's about all I'm going to do with that. I'm going to run that. And again, my syntax over here in this area is being generated automatically from this interactive playing around that I'm doing over here, which is pretty nifty. And it's also a way to learn how to program in SAS. So the program that I'm interested in here is the t-test. And this portion in green is actually commented out. So if you want to just put comments, you could do slashes and it'll make the text green. So I'm going to run this t-test with the little run guy. Get my face out of the way. Okay, and what I'm interested in here is, and this is true of statistics programs, it's going to give you some output that you might be wondering what it is. But I'm going to go to this portion of my output here, where it has the means for males and females. Females 1, male is 2. And I happen to know that from the code book. Ideally, there would be labels, but this data set did not do it that way. So I just happen to know 1 is female, 2 is male. It's alphabetical. So I've got 192 females, 216 males. The mean for females was 30.5. The mean for males was 27.0. Standard deviations are very similar at about 20. Okay. And so the difference between those two is 3.429. Okay, and it actually calculates a confidence interval around the difference. And notice that that confidence interval around the difference contains the value 0. Okay, so we've got a negative value and a positive value. It's not a good sign for my hypothesis here. And you could have actually seen this, that the males are actually on average younger than our females. My p-value is going to be down here, and I'm going to use the pooled estimate. The pooled estimate is when we're using the pooled variances. And whenever the variances are similar like they are here, it's appropriate to use this one here. So my p-value is 0.0914. It is not statistically significant. We fail to reject the null hypothesis. The null hypothesis here would have been that the two groups are equal, that men and women have the same age among the concussion population. And my hypothesis, my research hypothesis, was that women had an older age than men, or a younger age than men. Yeah, a reverse seems to be possibly true. However, what I would conclude from this, since it's not statistically significant, is that there is no difference. Okay, so it would be inappropriate for me to report out that there's a difference in the mean age in concussion because it's not statistically significant. I could have gotten means as different as what I see here just by chance alone. And my hypothesis doesn't seem like it holds much weight. They seem like, if anything, men are potentially a little bit younger. However, I can't conclude that either because I failed to reject the null hypothesis, which was a two-sided test. And the null hypothesis was that there was no difference between the two groups. And so my p-value, a little hard to see, 0.0914. And you can see here it actually calculates my t-value, my t-statistic, with degrees of freedom of 406. Well, that wouldn't even appear in your table. This would actually resolve to a z distribution. But in any case, it does calculate my t-value. But again, in practice, I'm really just going to look at my p-value here, 0.09, not statistically significant, okay? So that would be how I would perform a bivariate t-test just to explore my data. I'm not really interested more than to see if there's a significant association. Doesn't seem to be. So I can conclude that there's not really a strong association between sex and age. And that may be interesting later in analysis because I don't have to necessarily worry about confounding between sex and age, which we'll talk about as a concept next week. Okay, so let me set up a 2x2 table. And I'm going to now hypothesize that women are more likely to receive imaging for their concussion than are men. If you'll recall from the live session, my discussion was about whether or not people receive imaging as part of their treatment. And the standard would be that you receive imaging under most conditions when you're an adult, over 18. And then for children, more limited conditions that you would do imaging. Usually there'd have to be vomiting and other things that would necessitate imaging to see the extent of damage. The goal would be to minimize the exposure of radiation that happens with X-rays and CT scans and so on. So I am going to hypothesize that women are more likely to receive a CT scan than men, but I'm mostly just doing this to demonstrate the mechanics of this. So I'm going to go over to table analysis. And we've actually used this already for doing a frequency in last week's live session. But now I'm going to do a table analysis where I have both a row variable and a column variable. Okay, so in my 2x2 tables, usually I'll put my exposure as my row and my outcome as my column. In this case, we're not looking at a disease, but we're looking at the outcome of having received imaging. So I'm going to put sex as my row. Say okay, and I'm going to put any image down here, any imaging as my column variable. Okay, so I am going to set up a 2x2 table. Sex has 2 categories, and whether they received imaging also has 2 categories. I'm also going to make sure that it gives me observed frequencies. I'm also going to ask it for row percentages so that I can say for males and females what percent received imaging. It defaults to having the chi-square statistics. I'm glad about that. I'm going to avoid doing odds ratios and relative risk. Well, I'll go ahead and plug that in. But notice it allows me to do odds ratios and relative risk as a measurable fact here as well. So I'm going to run this. Now I got way more output than I want. But let's look at our 2x2 table. So again, females 1, males 2. Any image, no actually appears to the left, and then yes is the right. So it's a little flipped how I would maybe want to have it, but that's just because they do it numerically in order. But the point is that women, 69% received imaging, men, 71%. Just eyeballing this, I'm going to guess that this is not statistically significant just because those percentages are not very different. But I'm not using my eyeballs to do it. I'm going to perform a formal statistical test. I'm going to ignore all that graphing that happens. And notice my chi-square value is 0.3032, a little hard to interpret that. But don't forget, for a 2x2 table, our critical value is going to be over 3, in fact, 3.82. So definitely lower than that. And so my p-value is 0.5819, not even close. There's no association between sex and receipt of the imaging, okay? As I'm going through here, looking at associations between variables, I'm doing this more so for to see what the relationships are among my variables. And this is often what we do in analytic work where we say, okay, I'm not formally testing my main hypothesis here. I'm more just looking to see if there is an association between these two variables. And that would become important to know as we go into multivariate modeling to know what is related to what. It's a little unsatisfying so far that nothing's been statistically significant, but that's not our goal here. Our goal is to see what is associated with what. And ultimately, we're going to look to see if our goal is going to say what does predict getting imaging versus not getting imaging. So it looks like there's no difference there, but let's go back to a t-test. Now I'm going to get a little closer to my hypothesis, which is okay. So I'm going to look now at another 2-sample t-test, and this time my analysis variable is going to be age. Okay, that's our outcome or response variable. Our grouping variable, I'm going to do received imaging or not. And in this case, I would expect, I hope, that there's a very pronounced difference in the average age of those who do receive imaging versus those who do not. Again, guidelines would suggest that those who are older, it's okay to do imaging because the radiation exposure isn't as likely to have developmental impacts or to cause cancer risk. But there should be a difference. There should be that those who are older are more likely to have had imaging and vice versa. So let's run that formal test. Okay, and again here, so those who did have an image, the average age was 32, and the average age who didn't receive imaging was 20. So a 12-point difference in the means here. And I'm guessing you can guess that this is statistically significant. It is, but how do I know that? Well, if I look here at the p-values, p is less than 0.00001. I could say that this is highly statistically significant. Some people do say that. I would say, well, whatever was your criteria, alpha 0.05, we would just say it's statistically significant. But clearly there's a pretty big difference between those who receive imaging and don't in terms of mean age. And in fact, we also, from the same output, can get estimate of the difference of 12 points, which we see here. And the range of that difference based on the confidence interval is between -8 and -16. So there's somewhere between an 8 and a 16 year difference in those who receive imaging or not. So highly different, highly statistically significant. And so here's an example of where a t-test demonstrates a strong difference, where the null hypothesis was that the means were the same. The alternative hypothesis, or my research hypothesis, would be that they're different. And in fact, that older folks would be more likely to receive imaging, and that does seem to be, there does seem to be support for that, thank goodness. It's kind of a, yeah, duh hypothesis, but thankfully the overall effect of age is pretty strong, like I expected it to be. But we can see that formally here with the statistical test, that in fact there is a huge difference in age. And we could then report out that the average patient who receives imaging is around 32. The average patient who doesn't receive imaging is around 20. I may want to investigate further what the distributions are. And it's kind of neat that SAS shows us with plots, I didn't ask for it, but it did, the distributions of age for the two groups. And you can see the non-image group, the box plot here, this is where most of the people who didn't get an image are, the interquartile range. And then for those who did get an image, the interquartile range is over here. So this also is a nice visual representation of the difference between these two group means. So a t-test is a way to formally express the difference in these means. But there's other ways of visualizing this information as well. So that's a t-test, and that is a chi-square test. Again, t-tests are under the t-test tab. You'll want to make sure that you do a 2-sample t-test unless you've done a study design that you have paired data. And then our analysis variable will be a continuous measure, and your grouping variable will be some sort of dichotomous measure. For doing a contingency table or a 2x2 table, I'm going to do a table analysis and set up my rows and columns. And these would be 2 categorical variables. It could be 2x2, it could be 3x4, it could be any number of categories. And so that's where we would set up our chi-square test. All right, so that's my demonstration of a t-test and a chi-square test. And those are the bulk of what we would do in looking at bivariate analysis. We will discuss correlation between 2 continuous measures when we get to linear regression. But often what you'll see in table 2 of a study would be these tests done on 2 groups. And usually it's our outcome of interest and say, what are the differences in different characteristics of our population? And using the appropriate tests, whether it's chi-square or t-test, to make a determination whether or not those are statistically significantly different.